Dear students, I am Dr. Sudheer K. I welcome you to a series of classes in vector calculus. This will be useful for students of B.Sc Mathematics program doing the course Vector Calculus and to those who prepare for the various entrance examinations like IIT JAM and entrance examinations of other central universities. In today's class, we discuss two important concepts, namely the scalar field and the vector field. Before going into the actual definition, let us look at a real-life situation. Imagine that an electric heater is placed at one corner of a room. When the switch is turned on, heat spreads. At each point of the room, temperature can be measured. The temperature may vary from point to point. Temperature can be considered as a function of the position. At the point xyz, we can say the temperature is Txyz, which is a scalar function of the three variables x, y, and z. Now imagine that a strong magnet is placed above a table in a room. At each point in its surrounding, if you keep a magnetic needle, a deflection of the needle can be observed. The magnitude of the deflection and the direction of the needle depend on the position where the needle is placed. In other words, we say that the intensity of the magnetic field depends on the position. At the point xyz, we can say the magnetic field is f of xyz, which is a vector function of the three variables x, y, and z. In this context, let us introduce three definitions. Number one, domain. It's a subset of the two or three-dimensional space. If the subset is not specified, the domain is assumed to be the full of the real plane R2 or the real three-dimensional space R3. Number two, scalar field. It is a function that assigns a unique scalar value at each point of the domain. By a scalar, we mean either a real number or a complex number. 3. Vector field. It is a function that assigns a unique vector at each point of the domain. Now, when we look at the examples or real-life situations we considered, in the case of the heater placed in the room, the interior of the room is the domain. At each point of the domain, the temperature observed is the respective value of the scalar function. So, when the temperature observed at all points in the room are considered as a whole, that will give you the scalar field. In the case of the magnet placed in a room, the interior of the room is the domain. At each point of the domain, the magnetic field observed is the respective value of the vector function. So the vector field will be the collection of magnetic fields observed at different points in the room. Scalar fields define curves in two-dimensional planes. As an example, let us take fxy equal to x square minus y to be a scalar field. The equation fxy equal to 1, that is x square minus y equal to 1 or y equal to x square minus 1 will define a parabola. You can see this equation y equal to x square minus 1 will represent a parabola in the xy plane. Consider another function fxy equal to x square plus y square. The equation fxy equal to 1, that is x square plus y square equal to 1, will define a circle. It is a circle on the xy plane with center at origin and radius equal to 1. Similarly, fxy equal to c, where c is any constant, will represent a curve in the xy plane. Scalar fields can define surfaces in three-dimensional spaces. As an example, consider fxyz equal to x plus y plus z to be a scalar field. The equation fxyz equal to 1 represents a plane in the three-dimensional space. It is actually the plane passing through the points 1, 0, 0, 0, 1, 0 and 0, 0, 1. We can say x plus y plus z equal to 1 is the plane making intercepts of length 1 on the positive sides of x, y and z axis. Now consider the function fxyz equal to x square plus y square plus z square. If the equation fxyz equal to 1 is assumed, that is x square plus y square plus z square equal to 1, it will define a sphere in the three-dimensional space. The sphere has got center at origin and radius equal to 1 unit. Similarly, fxyz equal to c, where c is any constant, represents a surface in the three-dimensional space. An important concept related to a scalar field is the gradient. For the scalar field fxyz, the gradient is del f equal to partial derivative of f with respect to x I plus partial derivative of f with respect to y j plus partial derivative of f with respect to z k. That is del f equal to dou f by dou x I plus dou f by dou y j plus dou f by dou z k. From the definition itself, it is clear that the gradient of a scalar field is a vector field. Here, the coefficients of I, j and k will be functions of x, y and z. As an example, consider the scalar field fxyz equal to x square plus y square plus z square. Then fxyz equal to x square plus y square plus z square equal to 1 is a sphere with center at origin and radius equal to 1 unit. Let us calculate the gradient. Del f equal to partial derivative of x square plus y square plus z square with respect to x. That will be 2x only. 2xi plus the other partial derivatives can be found. So that will give you 2yj plus 2zk, or it's equal to 2 times xi plus yj plus zk. This will be a vector along the normal direction. Why? Because xi plus yj plus zk is the radius vector. Radius vector will be the vector from origin towards the surface of the sphere. So it will be along the normal direction to the surface of the sphere. So generally we can say, if fxyz equal to c is a surface, then at the point xyz on it, the gradient is a vector along the normal to the surface. Now a new definition: directional derivative at a point on a surface along a vector. Let fxyz be a scalar field and let A be a vector. The directional derivative at the point xyz on the surface fxyz equal to c along the vector A is del f dot u, where u equal to A by magnitude of A is the unit vector along A. Let us look at an example. Consider the surface x square minus 3y square plus z cube equal to 0. And let A be the vector 2i minus j plus 2k. We have to find the directional derivative at the point 2, 2, 2 along the vector A. It is easy to check that the point 2, 2, 2 is on the surface x square minus 3y square plus z cube equal to 0. You just have to substitute the values of x, y and z as 2, 2, 2. This expression will reduce to 0. The unit vector along A is A divided by magnitude of A, that is 2i minus j plus 2k divided by magnitude of 2i minus j plus 2k. Magnitude of 2i minus j plus 2k is 3. So u equal to 2i minus j plus 2k divided by 3. Del f equal to the partial derivative with respect to x will become 2x. Partial derivative with respect to y will become minus 6y. Partial derivative with respect to z will become 3z square. So del f equal to 2xi minus 6yj plus 3z square k. At the point 2, 2, 2, del f equal to, so we just substitute the values x equal to 2, y equal to 2 and z equal to 2 in this expression. Del f equal to 4i minus 12j plus 12k. So the directional derivative is dot product of del f and u. So it is dot product of 4i minus 12j plus 12k and 2i minus j plus 2k divided by 3, which can be calculated as 44 by 3. See, we know that the dot product will give the maximum value when the two vectors are in the same direction. So that will give you the directional derivative will be maximum along the normal to the surface. Why? Because gradient is along the normal. So if you take the vector A also along the normal to the surface, the directional derivative will become the maximum. Further discussion on the scalar and vector fields will be continued in the next class. Till then, thank you and bye.